Hello friends, welcome to Physics with Ben. Don't forget to subscribe, like, comment and share this video to those that need it. I promised a video on Hooke's law experiment and this is the video. You may love to click in the description box below to watch the video on all the theory on Hooke's law, all calculations on Hooke's law. And this particular experimental video is the last video series on this video. I wish you guys success in your exams. I deliberately kept this here so that I can teach us the setup for this experiment. So in Hooke's law experiment, in this particular experiment, I want to make two videos for this experiment. This is the first experiment. So this is the rectal stand. You need this, and these are the slotted masses for this particular experiment. This is 20 gram, 20 gram, 20 gram, 20 gram, and this, with the whole of this, is 50 gram. So we are going to set up the experiment. This is your rectal stand. How do you go about it? I will pick this thing up here and put it here. Then this, I will put it somewhere here, and this is a 100 cm ruler, or we call it a meter rule. The zero parts, the zero calibration will be on top, while the 100 calibration will be down. So I'm gonna hook it up here, and I'll adjust this to go right in here, and then I hook this up here, and then this I'll shoot it back here, and see what I'm doing to tighten the meter rule down here. Good. The next, I will hang this mass, this spring here, somewhere here. So I'm going to use this for that purpose. So my spring is hung in the right place. Good. So I will tighten this from this end so that it will hold the meter rope up and down here. Watch me. Good. We are good to go. So I'm done setting the apparatus for the experiment. It is time to perform the experiment. So you need your graph sheets, you need your writing materials, and then for the sake of this experiment, I'm making use of this book. If you have this book with you, I recommend this book to you by this author. You can find this experiment in this particular page, page 80 and page 81, then page 82. So without wasting much time, let us go straight to the business of the day. So as usual, you may love to screenshot this. This is the question we are performing experiment with. Suspend the given spiral spring vertically as shown in the diagram. Attach a scale pan and note the position of the pointer on the meter rule. Add mass M is equals to 70 grams to the scale pan and note the new position of the pointer. Determine the extension E produced. Repeat the experiment for with 90, that's a typo error, 90, 110, 130, and 50, 150 grams respectively. In each case, determine the extension. Without wasting more time, just screenshot this or play back this so that you can know what I'm doing. Good. So as we have been doing in the other videos, we highlight where we need for the table of values. So you can see those places highlighted with the black pen are the areas where we need to concentrate to get our table of values. I'm doing this because I have produced so much videos on how to determine table of values from experiment. So go back and watch all of those videos and then come back and do this class activity. I will show us next the table of values for this particular experiment. Thank you. So based on the information we have here, as you can see, you can screenshot. Based on this information, this is the table of values that we have here for this experiment. I always tell us in all the videos I have done on experiment that table of values carries the highest mark. So we are going to run the experiment 5 times with the first mass, second, third, fourth, and fifth. X naught is constant throughout. I was supposed to record X naught on top of the table of values here, but I did it here deliberately to give clarification to this. X naught stands for the initial position of the pointer. At this point, if you can look at it very well, the initial position of the pointer is at 61. So the pointer is at 61. So we are going to record 61.00. 61.00. 61.00. 61.00. 61.00. As simple as ABC. So to proceed, I told us initially this is 20 gram, 20 gram, 20 gram, and 20 gram. The whole of this with this is 50 gram. So the first value said we should slot 70. The first instruction said we slot 70. So this is 50 plus 20, that is 70. So we hang it here. I will take the new position for the pointer. The pointer is pointing at 61. Sorry, that is 64. It's pointing at 64. So record 64. 64.00 is the new position for the pointer. So we 64, the extension produced is x minus x naught. So we have 3.00, that is 64. 64 minus 61, that will give us 3. So we have 3.00 is the extension. The next, we are asked to slot 90. So this is 50, 60, 70, 80, 90. When we slotted 90, what was the new position? Let's take it close. The new position is 64.5.6.7.8. 64.8. And so we record 64.8 minus 61, which is constant throughout. Then we get a new result there. And so the new extension when a mass of 90 grams was hung is 3.8. You can see that we are actually verifying Hooke's law right now. Increase in the force will cause extension to increase. That is the relationship between mass and extension, a direct relationship, an increase relationship, or a decrease relationship. So next, we are to slot 110. What is here is 90. 90 plus 20 will give us 110. So this is 20 grams. We slot it here. We hang it. And we get a new position. Make sure the mass is not oscillating before you take your reading. I can see 65.5. But let's take the camera closer. That is 65.6. So report 65.00. 65. So our new extension is a 4.00. 4.00. Next up, we have to slot 130 grams. So 110 plus 20 will give us 130 grams. That is 130. It has returned back to its position 61, telling us that this spring is actually an elastic material. So this is the mass of 130. Let's look at the new position. For my own end, you must make sure that the mass is not oscillating. You can't take a reading when it is bouncing like this. You have to make sure that that is not happening. So you hang it gently. And then take your hand away like that. So I'm having that is 66.1.2.3.4. 66.4 is what I'm having. But let's take our camera close and see what we have there. So I was correct, 66.4. Good. And so our new extension for that is this minus this, we got 5.40. Telling us that F is actually directly proportional to the extension, and F is equal to what? KE. Verified. So the last but not the least is a 50 gram, 150 gram. For 150 gram, we can choose to add 2 of this and remove this 20 grams. This is 50, this is 100, and this is 150. This is 150. So we hang it and get the position, the new position. So from my own end, I'm having 67 points. Take note, you don't stand like this to read. You don't stand like this to read. You bend down, you read this way. So I'm having a 67.1.2. 67.2. Let's read it together. So 67.1.2. Good. So we have our table of values partially complete now. So this is, if you observe, the mass is increasing down and the extension is increasing down from 3.0 to 3.8 down to 6.2. So the trend of this experiment is increase. Going up is decrease. Verifying that the force is directly proportional to the extension, where K is the stiffness of the spring or the elastic constant. The other part of the experiment reads that we should hang this 150 mass, and we should hang the 150 mass. Can you see that? With the load of 150 on the scale pan, set the spring into small vertical oscillation and determine the time for 10 complete oscillation. Also, do it for 100 grams. So we are going to have another section for this table down here, where we add, that's immediately below down here, where we add 100.00 to it, and then complete that. Oh, sorry, but let's just leave it here. So we are going to find the time for 10 complete oscillations. This is my stopwatch, and we're gonna do that. So the spin will go up and come down. That is 1 oscillation, which is equal to 2 pi radians. Watch the video in check the video links in the description box below and watch the theory and all the calculations, and then you understand what I'm talking about here. So let's go. Release it gently. 1, 2, 3, 4. Let's do it again. Take it too fast. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 0. I got 4 seconds. I got 4 seconds. I got 4 seconds. Let's try that again and see. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 4 seconds. So the time for 20 complete oscillation, I got 4.00 seconds when the mass was 450. So if I take this, I will repeat that procedure. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see that I decreased the mass and the oscillation was faster, the frequency was faster. I got 0.3 seconds. Let's do it again. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do it again. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 3 seconds. So when the mass was this, I got 3.00 seconds. So how do we get the period? The period is simply the time. The period is the time. This time divided by 10 oscillations, we get a period. So we have 4 divided by 10. We have 0.40 here, and then we have 3 divided by 10. We have 0.30, 0.40. So this is the information for the second part of the experiment. So to this, we have come to the end of the experiment. Next up is to plot the graph and do all the deductions as can be seen here.